In this video, we are going to learn all about vectors, which are one of the building blocks of this course. Starting with the definition, a vector is a quantity that has both a magnitude and a direction. So vectors represent two pieces of information. We use an arrow to represent a vector where the length is equivalent to the magnitude and the arrow points in the direction of the vector. So visually, we're going to see vectors look like this. So we have a line segment with an arrow at one end. The length of that line segment would be its magnitude, and the arrow indicates the direction. Right? So there's our example of a vector. Notation. There are two different notations that we will use throughout this course to represent vectors. The first is a boldface letter. That's easier when we're typing, so often when we're given questions, vectors will be represented with that boldface letter. And when we're writing out the mathematics, we'll use the letter with a vector hat above it. It's easier to write out. Okay, so these are interchangeable, but both notations represent vectors. As far as applications of vectors, quantities such as displacement, velocity, and force can be represented by vectors. And we're going to see these applications throughout the course in different aspects. Now, two vectors are said to be equal if and only if they have the same magnitude and direction, regardless of their position. So this is important here. And that means that vectors are not fixed in space. So if we draw a vector, and let me make it so I can duplicate this. So that vector and that vector, if I move it up there, and if I move it over here, all of those vectors are equivalent. Even though they are at different places on the page, the position of the vector does not matter. As long as the vectors have the same magnitude and the same direction, we consider them to be equivalent. If a vector is drawn with initial point A, which is x1, y1, z1, and terminal point B, which is x2, y2, z2, then the displacement or direction vector is, so we're creating a vector from point A to point B, and the way we're going to do that algebraically, we'll use vector brackets, so we're going to have x2 minus x1, y2 minus y1, z2 minus z1. Right? So the important part to represent here is that we are taking the terminal point minus the initial point. And we're looking at the x component, the y component, and the z component all separately to create the vector. So a word I use there that's going to be important, these are all considered components of the vector. So in this case, this is a three-dimensional vector, so there are three components, an x, a y, and a z. We can have a two-dimensional vector, we can have a four-dimensional, five-dimensional vector. Vectors are not restricted to just 3 dimensions. Now, an important vector that we're going to see throughout the course is the zero vector, which is denoted with a bold 0 or 0 with a vector hat above it. And that has a length of 0 and an undefined direction. Important when we are trying to denote the zero vector, just writing the number 0 is not sufficient because 0 is a scalar, which we'll talk about more in the coming videos, whereas a vector needs to be notated as such. So either with bold or with a vector hat. So if we find the vector representation represented by the directed line segment with initial point 320 and terminal point 415. So this is a great opportunity. Pause the video, check in, see how you're understanding the material so far, and then play the video to see how you did. Okay, so we'll call this vector V. So the terminal point minus the initial point, so we'll have 4 minus 3, 1 minus 2, 5 minus 0. So vector V will be 1, -1, 5. So what this vector represents is if we were to start this vector at the origin, the vector would end at the point 1, -1, 5. Okay, even though we are creating the vector between the point 320 and 415, the components tell us if we were to start this vector at the origin, where would the terminal point of that vector be? Another piece is the magnitude, right? We talked about how vectors represent a magnitude and a direction. So we need to figure out how we're going to find that magnitude algebraically. So as far as notation for magnitude, two different notations. So it can either be a single or a double bar around the vector will indicate that we are looking for the magnitude or the length of the vector. It's interchangeable. Really, it's a matter of preference. You will see both based on the problems that you're given. I do know the single bar represents absolute value, but we have to understand that v is a vector, not just a number. So we're not going to treat it like the traditional absolute value. But in a sense, it is related, since absolute value is a measure of distance from 0 on the number line. Magnitude is a measure of length or distance of the vector. So let v be a1, a2, a3. Then the magnitude of v is defined by. Okay, so I went single bar here for this definition. So that's going to be the square root of a1 squared plus a2 squared plus a3 squared. The distance formula, right? If this is where the vector would end, if we were to start it at the origin, then really we're finding the distance from the point a1, a2, a3 to the origin, 0, 0, 0. So it would be a1 minus 0, a2 minus 0, a3 minus 0 squared. And again, all of this relates back to the Pythagorean theorem. So find the magnitude of the vector v equals -3, 5, 12. Again, pause, complete this yourself, play the video and see how you did. Okay, so magnitude of v is the square root of -3 squared plus 5 squared plus 12 squared. So magnitude of v is the square root of 9 plus 25 plus 144. So the magnitude of v is the square root of, let's see, 178. Okay, so that represents the length of the vector. So now we're going to look at vector operations. That is vector addition, vector subtraction, and scalar multiplication. We'll start geometrically so we can visually see what is going on for each of the operations, and we'll follow that up by defining them algebraically. So vector addition, position the initial point of v at the terminal point of u. The sum u plus v is the vector from the initial point of u to the terminal point of v. So geometrically or graphically, this is what it's going to look like. We're going to take vector v and we're going to move it so that the initial point of v is at the terminal point of u. So the tail to the tip. Okay, so the tail of vector v to the tip of vector u. And then the vector we're looking for, u plus v, is going to start at the initial point of u and go to the terminal point of v. Let's see if I could adjust that terminal point just a little bit. Make it a little better. There we go. Okay, so that is the vector u plus v. Now addition is commutative, so we could have done v plus u, and in that case, we would have taken vector u and moved the initial point of u to the terminal point of v, so the tail of u to the tip of v, and notice we get the same result. There. Okay, so if we complete the addition both ways, we do create a parallelogram, and the sum u plus v is the diagonal of the parallelogram. Scalar multiplication. If c is a scalar and v is a vector, then the scalar multiple c times vector v is the vector whose length is absolute value of c times the length of v. Now in this case it is absolute value since c is a scalar, it's a number as opposed to a vector, so it's not a magnitude. So scalar multiplication, before we start defining the cases underneath, if we look, so let's take vector v. So remember, vectors are not fixed in space, so we can move vector v there. So that's vector v. So if we doubled it, right, so there we have vector v. So now let's take another one, I'll lay it on top, and then let's double it. So we'll go 3 more to the right, and then down 1, 2, 3, 4, 5, 6 more. Okay, and then that now is vector 2v. And if we had a negative scalar, so let's say we took vector v there. Again, all of these vector v's are equivalent because they're not fixed in space. So negative v, all I'd have to do is change the direction. So I'll just draw over this one. So that would be negative v. Okay, so scalar multiplication, if the scalar is positive, going to be in the same direction. If the scalar is negative, the vector is going to point in the opposite direction. So that's what our cases down here are defining. So if c is greater than 0, then CV will be in the same direction. Same direction. If the scalar is negative, then CV will be in the opposite direction. And if c equals 0, or vector v is the 0 vector, then CV will be the 0 vector as well. And then vector subtraction is just addition of a negative vector. So u minus v is really just vector u plus negative v, right? So we would take u, we would take negative v, and we would do exactly what we did with the parallelogram up there. Now, the note on the side, two vectors are parallel if they are scalar multiples of each other. So on our graph, vector v, vector 2v, and negative v are all considered parallel vectors. Right? It doesn't matter if they're in the same direction or opposite directions. If they are scalar multiples, mathematically we define those as parallel vectors. Right? So v, 2v, negative v would all be examples of parallel vectors here. Okay, so here's an example for you to try. Pause the video, complete the 3, play the video, and see how you did. Okay, so a minus b. So I'm going to move vector b here. But I know I did it the wrong way where their terminal points are matching, but that's because negative b then goes the opposite direction. So then a minus b, we go from the initial point to the terminal point there. So that's going to be a minus b. And then we have 2a. So again, not fixed in space. So let's move it there. So that's a. So then 2a, we go over 2, up 1, 2, 3, 4. So there's 2a. And then 2a plus b, so then we can slide vector b there. So that's vector, whoop, wrong spot. See, I can make mistakes every once in a while. I don't want the initial points to be there. I want to move b's initial point to the terminal point of 2a. That's better. So that's b. So then 2a plus b, we start at the initial point, go to the terminal point of b, and there we have 2a plus b. Okay, so this is how vector addition, subtraction, and scalar multiplication works geometrically or graphically. So now let's define it algebraically. So if we have two vectors, u being a1, a2, a3, v being b1, b2, b3, and c be a real number, then we define vector addition. So u plus v is going to be a1 plus b1, a2 plus b2, a3 plus B3. We add all the like components. So the x components, the y components, the z components. Then vector subtraction, so u minus v is a1 minus b1, a2 minus b2, a3 minus b3. Now we subtract the like components. And then scalar multiplication, so if we have c times vector u, so that's going to be ca1, ca2, ca3. So we multiply each component by the scalar c. So if we let a be the vector 2, 3, negative 1, and b is the vector 4, negative 2, 5, compute the following. So a plus b. So adding the like components. So we have 2 plus 4, so that will be 6. 3 plus negative 2, which will be 1. And negative 1 plus 5, which will be 4. A minus b. So we have 2 minus 4, which will give us negative 2. 3 minus negative 2, which will give us 5. Negative 1 minus 5 is negative 6. So notice we can only add and subtract vectors in the same dimension. Right? We cannot add a two-dimensional vector to a three-dimensional vector, since there wouldn't be like components for both vectors. And then some scalar multiplication, 2a. So we're going to multiply each component of a by 2. So that'll be 2 times 2, which is 4. 2 times 3, which is 6. 2 times negative 1, which is negative 2. And then we're going to take that vector and add it to 3b. So let's see if we can just do this in our head. So 4 plus 3 times 4 is 12, so that's 16. 6 plus 3 times negative 2 is negative 6, so 0. And negative 2 plus 3 times 5 is 15. So negative 2 plus 15, 13. Okay, so algebraically, vector addition, vector subtraction, and vector scalar multiplication is not really too difficult. It works out quite nicely. Now, the last type of vector that we have to define is called a unit vector. And a unit vector is a vector that has a magnitude of 1. Unit vectors are going to be really important for us because they indicate a direction, but the magnitude of 1 means that in computations, the magnitude is not going to have an effect on the result. Okay, so it's a way for us to indicate direction while just creating a magnitude of 1. So think multiplying by a magnitude of 1 won't change an answer. Now, given a non-zero vector v, the unit vector u in the same direction is found by dividing v by its magnitude. Okay, so this is the process for finding a unit vector. So we have a vector v, we want to find the unit vector u. So we're going to take vector v and divide it by its magnitude. And you can write that differently. You could say 1 over magnitude of v times vector v as well. Okay, so we have to be able to find the magnitude of a vector, and then we divide the vector by its own magnitude. We're going to create a unit vector, which has the same direction, but the magnitude will be 1. So find the unit vector in the direction of negative 1, 6, 2. Okay, so if we call this vector v, do that here, call this vector v. So the magnitude of v then is the square root of negative 1 squared plus 6 squared plus 2 squared. So that's the square root of 1 plus 36 plus 4, which is the square root of 41. So the unit vector, we'll call u in this case, just to match the definition. The unit vector will be 1 divided by the square root of 41 times the vector negative 1, 6, 2. So if we distribute out that scalar, it would be negative 1 over the square root of 41, 6 over the square root of 41, 2 over the square root of 41. And we can check, if we find the magnitude of this vector, we can check pretty quickly that it will be 1. Right? If we squared each component, so we'd have 1 over 41 plus 36 over 41 plus 4 over 41. 36 plus 4 plus 1. 41 over 41 is 1. Square root of 1 is 1. Right? So write that out if you find that helpful, but you can see that the magnitude of this vector will be 1. So we did this correctly. Now, working off of unit vectors, the vectors I being 1, 0, 0, j, 0, 1, 0, and k, 0, 0, 1 are called the standard basis vectors. So essentially what these are, they are the 3 unit vectors in the direction of each of our axes. So I goes in the direction of the x-axis, j goes in the direction of the y-axis, k goes in the direction of the z-axis. What that means for us is that any vector in 3 space can be expressed as a linear combination of the vectors I, j, and or k. So throughout this video, we've been using vector brackets. We're going to introduce a second way to write a vector, and that's going to be as a combination of i's, j's, and k's. So the vector -1, 6, 2 can be expressed as -1i plus 6j plus 2k. Okay, which means that -1 is in the x direction, so the I direction. We scale I by -1. 6 is the direction we move along the y-axis, so we're going to scale j, the unit vector, along the y-axis by 6. And then 2 is how much we move along the z-axis for this vector. So k being the unit vector along the z-axis, we're going to scale it by 2. Okay, and just helpful for our diagram, you might want to include, right, magnitude of I equals magnitude of j equals magnitude of k, which is equal to 1. Right, so this combination of i's, j's, and or k's is a second way that we now have to write a vector. So we have vector brackets, which is definitely nice. Most of you will prefer this way, but combinations of i's, j's, and k's will be a second way that questions can be presented to us or that we can write a vector out. So let's look at vector addition, subtraction, scalar multiplication, unit vector with this new notation of i's, j's, and k's. So A is 3i minus 5j plus k. B is 6i minus 2k. Find the following. A minus B. Okay, so 3i, 6i. So we're only dealing with the like component still. Now we just have to match i's, j's, and k's. So this is going to be 3 minus 6, so negative 3i. And then negative 5j, there is no j component of vector B, so then minus 5j. And then 1k minus negative 2k, so plus 3k. And we can't combine these. They are not like terms, right? We have i's, we have j's, and we have k's now as far as the components of the vector. Right? I's represent the x component of the vector, j is the y, k is the z. So now 3a plus b. So let's just find 3a first. So 3a is 9i minus 15j plus 3k. So adding that to b, so we get 15i minus 15j, and then plus k. And then the unit vector in the direction of A. Okay, so that means that U is vector A divided by its magnitude. So the magnitude of vector A is the square root of 3 squared plus negative 5 squared plus 1 squared. So magnitude of vector A is the square root of 9 plus 25 plus 1. So magnitude of A is the square root of 35. So then the unit vector we're looking for is 1 over the square root of 35 times the vector 3i minus 5j plus k. Which again, we could, right? We could distribute it out. So 3 over the square root of 35i minus 5 over square root of 35j plus 1 over the square root of 35k. Just a matter of preference. Okay, so we covered a lot about vectors. Each piece is important, and the more that we work with each part of this lesson, we're going to get more comfortable, right? So what is a vector? How is it defined? How do we graph them? How do we perform operations with them? And then that last piece of being a unit vector is really important for us as well.